Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. We continue with our lectures on functions of several variables. Formally, this is chapter 15 of the book I prefer to follow for this course, which is Sydsaeter and Hammond, the fourth edition of this book. Okay, now all students can recall that in the previous lecture of functions of several variables, we had talked about the introduction to the concept of functions in several variables. We had defined the function f as the function of x and y, and we had also looked at some examples in microeconomics and statistics based on functions of several variables. We had also learned how to find the domain of a function of two variables. And we had also done some practice questions based on the same concept. Now, in this particular lecture, we intend to look at geometrical representation, geometric representations of the functions of several variables. So, in this particular lecture, I will help all students to visualize how the three-dimensional space looks like. Okay, so we can write an equation f of xy equal to c in two variables x and y can be represented by a point set in the plane called the graph of the equation. An equation f of xy equal to c in two variables x and y can be represented by a point set in the plane called the graph of the equation. Okay, so for example, if I have to plot the graph z as a function of x and y, it will have how many axes? It will have three axes. So the diagram is going to look somewhat like this. You can see it's a three-dimensional figure: x-axis, y-axis, z-axis. Okay, how will I show a point x equal to a? A point x equal to a will be on the x-axis. What will be the coordinate of this point? A 0, 0. A point on the y-axis would be a point of the form 0, b 0, and the z-axis is capturing the height. If you look at it properly, z-axis is capturing the height or the level. So this is going to be, suppose we have a point C, so this is going to be 0, 0, C. And what is this point? This is nothing but my origin, 0, 0, 0. So you can see a graph in the three-dimensional space. Z is a function of x and y, and z is going to capture what is the height of the function. So a function of x and y will be in the space, but that function is at what height? It will be captured by z. Okay, so let us look at some economic applications based on this particular concept. Okay, so some economic examples. Now in microeconomics, all of us know the concept of budget lines. From high school economics and from my course introductory microeconomics, all of us know the basic concept of budget lines. So now the only difference is instead of 2 commodities, now we have 3 commodities. So suppose a person spends an amount M on the purchase of 3 commodities. Instead of 2 commodities, now we have 3 commodities whose prices are P, Q and R per unit respectively. Okay, so if the person buys X units of the first commodity, Y units of the second commodity, and Z units of the third commodity, what will my budget line be? We can write the budget line. My budget line, now this will actually be called a budget plane. So what will my budget plane? Because now it's 3 dimension. So P times X plus Q times Y plus R times Z equal to the income of the consumer, which is N. Now all students can recall from introductory microeconomics that when we only have 2 commodities, X and Y with prices P and Q, what is the budget line? It's nothing but Px plus Qy equal to the income of the consumer. So this will be a line in the 2-dimensional space. This is going to be X, this is going to be Y, this is my budget line. And all of us know budget lines are downward sloping. But now, how will I plot the budget plane? This is something new, because now we have 3 dimensions: X-axis, Y-axis and Z-axis. So if I erase the stuff which we have learned in the basic introductory microeconomics, which was just done to relate concepts to all students, if I actually draw the diagram of the budget plane, how is it going to look like now? So the diagram of the budget plane will be somewhat like this. This is my Z-axis, X-axis, Y-axis. What will be a point on the X-axis? If I put Y and Z as 0, what is X? M by P. So this will be my point M by P, 0, 0. If I put X and Z as 0, Y will be M by Q, 0, M by Q, 0. And if I put Y and X as 0, I get Z as M by R, 0, 0, M by R. Now these intercepts on the X, Y and Z axis will give us what is the maximum amount of good X I can buy, or what is the maximum amount of good Y I can buy, or what is the maximum amount of good Z I can buy given my constant and fixed income M. So clearly if I join them, you can see that there is a plane getting formed. There is a plane getting formed in the 3D space. This is called the budget plane. So the objective of this lecture is to help the students to visualize how the same concepts which you have learned in the 2-dimensional space look like in the 3D space. This is the only objective of this particular lecture. You need to understand whatever concepts you have learned in the two-dimensional space, how will they look like in higher dimensions like the three-dimensional space. Obviously, I can't show you in the lecture 4-dimension, 5-dimension, they are out of reach. Because on a piece of paper, the maximum dimensions you can possibly plot is the three-dimensional space. Okay, similarly, I can take another example. Example 2. Now recall, what is the equation of a circle? Equation of a circle centered at 0, 0 with radius equal to 2 is x square plus y square equal to 4. This is the equation of a circle with center at 0, 0 and radius equal to 2. Now this will be a two-dimensional figure. Why? Because if I plot it, x-axis, y-axis, and if I plot it, this is my origin, radius is 2. But now guys, if I talk about a sphere, now consider the equation of a sphere. Okay, sphere which is centered at 0, 0, 0 and radius equal to 2. Now remember, sphere is a 3D figure. This is now going to be 3-dimensional. Equation will be x square plus y square plus z square equal to 4. And if I plot it, how is it going to look like? X-axis, y-axis, z-axis. This is my origin 0, 0, 0. And you will see that there is a disk around it. If you close your eyes and imagine, you can imagine a disk. Imagine that in the 3D space, there is a disk which is there. So that disk will be nothing but a sphere. And what will be the points? This will be 2, 0, 0, 0, 2, 0, and this will be 0, 0, 2. Okay, and now instead of plotting this, suppose I have to plot this equation, x square plus y square plus z square less than equal to 4. Now less than equal to 4 is going to include all the volume inside it. So again, if you imagine, it's going to look like a ball now. It's going to look like a spherical ball. So you can think of it, this would be the equation of a spherical solid ball. Because it will also include all the area inside the boundary, which you can think of as the mass of the ball. X square plus y square plus z square equal to 4 will only give you the boundary of the spherical ball. But if I take all the region less than equal to 4, it's going to give me the whole mass of the solid ball. So now again, why are we doing all this? Because you need to visualize how things change when you move from 2-dimension to 3-dimension. This lecture will only help you to graphically understand how concepts work like in the 3-dimension space. The same equation you can see in the 2-dimension gives you a circle. The same equation in the 3-dimension gives you a sphere, a disk. And if in case you plot this, you get the whole ball. That means the boundary of the ball and the mass inside the ball. So if you look at the equation of Earth, the Earth is also a sphere. planet Earth is also a sphere. So its equation would somewhat resemble this equation mathematically, if we look at it in 3 dimensions. Okay, and now let me come to the main concept. We now talk about the concept of level curves. So our heading now is level curves in the 3D space. So let's write the definition of the level curve. Consider z as a function of x and y when the graph of this function in the 3-dimensional space is cut by a horizontal plane, z equal to c. The intersection gives us the level curve for the function f at the height c. So therefore we can say equation of the level curve is f of xy equal to c. Now let me help you to understand this visually. So if you look at the diagram, look at the 3-dimensional space. All of you can look at the 3-dimensional space. Now suppose I have this function f of x comma y which is floating in the space. For example, think of the function like this, somewhat floating in the space like this. Now this is my function z as a function of x and y. I have just hypothetically taken a function. And now imagine that there is a piece of paper in the 3D space. So I am drawing it in red color, the piece of paper which you can see. You can see that there is a piece of paper which I have drawn in the 3D space. This is nothing but my plane. You can imagine that there is a curve in the 3D space, and this curve is cut by a plane. The plane is nothing but z equal to c. Now you can clearly see that where is this plane cutting the curve? You can see that at this point and at this point and at this point and at this point, you can see that it is cutting, or I can superimpose on it for more clarity. Suppose my curve is like this. Let me draw the curve again in black color to help students to visualize this. So somewhat like this. This is my curve z equal to f of xy. Now this curve which is floating in the 3-dimensional space is cut by the plane z equal to c. So you can see that there is a hole which we can have where the curve is cutting the paper. So this is nothing but the level curve. If I draw the base of it somewhere, so this height is how much? This height is c, but the base will be somewhere here. So again, if you are able to understand the diagram, that's well and fine. But if you listen to what I am trying to convey, there is a curve z equal to f of xy which is floating in the 3D space. Now you can think of a paper, a piece of paper in the 3D space at a height of c. C is the height. Now that height at which the paper is cutting the curve is going to give you the level curve for that particular function. So level curve will be the point of intersection of the function with the plane at a given height. And in this case, the height is nothing but c. So imagine that there is a curve and that curve is intersecting the plane at a height of c in the 3D space, where c can be any number. That is going to give you the level curve. Okay, so I hope all students have understood. If I ask you what is the equation of a level curve, it's very simple. Equation of the level curve is nothing but f of xy equal to c. So I hope all students have understood the basic concept of level curves and have no doubts. Okay, let's now move forward. Let's do a practice question. The practice question makes the concept of level curves more easy to understand. Consider the function z equal to f of xy equal to x square plus y square. Draw the level curves for this function. Draw the level curves for this function. So what is the equation of the level curve? Equation of the level curve is f of xy equal to c. What is f of xy? X square plus y square equal to c. So this is the equation of the circle with the center at 0, 0. The center is at 0, 0 and radius is root c. So if I draw the level curve, guys, how will the level curve look like? The level curve, you have a family of level curves. As you keep on changing the values of c, you will get different level curves. So the center is at 0, 0. You can see I have drawn one level curve. Okay, this is the level curve when c is equal to 1 because radius is 1. If I increase the value of c to 2, I get another level curve. If I further increase the value of c, I get even higher level curve. So you can clearly see that all these are level curves. I can write family of level curves. That means if you are ever going to plot x square plus y square in the 3-dimensional space, what will be the level curves? The level curves will be nothing but circles with center at 0, 0 and radius equal to square root of c. These will be the level curves if you go to plot the diagram in the 3-dimensional space. Okay, and similarly, if I take another example, this was question number 1. If I look at another question, now this question is again based on the production function. Suppose y is a function of capital and labor, where y denotes the number of units produced by a firm where K is the capital and L is the labor. Then how will the level curve look like? So in this case, we can say a level curve for the above production function will be f of KL equal to a constant y0, where y0 is a constant. Now, do you all know what is this equation called as? If my production function f of KL is equal to y0, it simply means this curve gives all combinations, this curve gives all combinations of capital and labor such that output is constant. Now, what is this curve called in microeconomics? It is called a isoquant. All students can recall from the basic microeconomics theory, all combinations of two goods which give the consumer same level of satisfaction are called indifference curves. Similarly, all combinations of two factors of production, capital and labor, which give you the same level of output is called an isoquant. So for this production function y equal to f of KL, my level curves will be nothing but the isoquant. So if I draw the diagram, remember the level curves will always be in the two-dimensional space. If you draw the graph of this function, it's going to be in the three-dimensional space. But if you draw the level curve of this function, it's going to be in the two-dimensional space. Labor, capital, these are my isoquants. They are like the indifference curves. Downward sloping and convex to the origin like the indifference curves. So these are going to be my family of level curves. And all of us know higher the isoquant, higher the output. Always remember, there's another thing you learn from this lecture. Level curves are drawn in the two-dimensional space, but the graph of the function will be in the three-dimensional space. If I draw the graph of y as a function of capital and labor, it will come in the three-dimensional space. Labor, capital, output. The graph will come in the 3D space, but the level curves will come in the 2D space. Okay, so we can take an example. For example, suppose I give you the production function. Suppose the production function is Q equal to 5 K to the power 1 by 3 L to the power 2 by 3. This is my production function. The question asks you draw the level curve for output equal to 10 units. So how will you draw the level curve? 5K to the power 1 by 3 L to the power 2 by 3, you will put it equal to 10. So this implies this expression comes out as 2. I can take the cube on both sides. Cubing both sides. What do I get? KL square is equal to 8, which implies what is K? 8 upon L square. This is nothing but the equation of a hyperbola. All of you can recall this from my MME 1 course. If you plot this equation, it's going to look like a hyperbola, rectangular hyperbola. This is nothing but a rectangular hyperbola, and this gives us the isoquant. So my level curve for this question is an isoquant at output equal to 10 units. So this was one such example. You were given the production function. The question asks you draw the level curve for output equal to 10 units. You equate it equal to 10, do some simple algebra, solve it, you get rectangular hyperbola. Okay, and there is one more type of question which comes. So let's practice this question as well. Show that all the points x comma y satisfying x into y equal to 3 lie on a level curve for the function g of xy equal to 3 times xy plus 1 ka square upon x4 y4 minus 1. So we need to show that all the points x comma y such that x into y is 3 lie on a level curve for the given function. So guys, if I put xy equal to 3 in g of xy, I should be getting a constant, because what is the equation of a level curve? In general, equation of a level curve is f of xy coming out to be a constant c. So if I put xy equal to 3 in the function g of xy, I should be getting a constant. So 3 times xy is 3 plus 1 ka square upon x4 y4, I can write xy to the power 4 minus 1. So xy is nothing but 3. It comes out as 48 by 80, which is equal to 3 by 5. So how do I interpret this? So this means for all the pairs x comma y such that xy is 3, the value of g of xy is a constant equal to 3 by 5. I can say this means that x into y equal to 3 is the level curve for the function g of xy at the height of how much? 3 by 5. This simply means that xy equal to 3 is the level curve for the function g of xy at a height of 3 by 5. So this is another way in which a question can be asked regarding the level curve. So this is where I intend to stop in this particular lecture. The objective of this lecture was to help students visualize how concepts in economics look like in the three-dimensional space. And we have also covered a very important concept called level curves in the three-dimensional space, where we have learned that the graph of the function will be formed in the three-dimensional space, but the level curve of a 3D figure will be formed in the two-dimensional space. So this is where I stop. I hope all students have enjoyed this lecture. Now in the next lecture, we will discuss the concept of continuity for functions in several variables. So any doubt students have in this lecture, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofelconomics@gmail.com. So this is where I stop in this lecture.